Hi, everyone. Thanks for coming to the Roads to Research session today. My name is Vanessa. I work in the Office of Research, and I'd just like to invite you to help yourself to the coffee if you haven't already, and just be aware that this presentation is being recorded today. And we're really happy to have R2R Dallimore here to talk about something that we all tend to think about if we live on the BC coast. She's a faculty member with the School of Environment and Sustainability, and the title of her presentation is Marine Science for Sustainable Planning Along BC's Earthquake-Prone Coast. Thanks, Audrey.
Thanks, Vanessa. Well, good afternoon, everybody, and thanks for sacrificing your lunch hour to come and talk to us a little bit about earthquakes. And also during the presentation, we're going to be talking about the earthquakes that we've been reading about and hearing about over the last number of years. There seems to be quite a few more coming. We're going to talk about that. Are there really more earthquakes, or is it just that CNN is making us more aware of them? What the seismic hazard and risk is along the British Columbia coast. And we're going to talk a little bit about a research program I've been involved with for the past 10 years, started when I was 29. It's true. And the last 5 or 6 years, that research program has been placed here at Royal Roads University. And many thanks to, whoops. Oh dear, I had an animation. Deb, I had a picture of you. Do you know what? Excuse me, just 1 second here. I'm just wondering, can we stop for a moment? This is a previous version of this talk, just 2 seconds. I put an animation of Deb on this. Excuse me, this is what you tell the students never to do. Load the wrong talk. 2 seconds. Huh.
Load it, or do you want me to
I
grab?
think, there we go. So here comes the money picture where I realized I was in the wrong, there we go. There is our own Deborah Zorns, the manager of research, and these ladies in Deborah's research office are certainly the main reason behind the funding that we've been able to generate for this somewhat expensive research. Deb is so committed, she came to sea with us, not last summer, but the summer before, and there she is on the ship getting trained. And this past summer, she was so popular with the rest of my crew. She did such a fantastic job. Nobody cared about me. So how come Deb's not coming back with us? So Deb and her team in the research office have been instrumental in helping us to get funding for this program, research program, for the last 5 years. We've been funded by grants from Royal Roads University, Natural Sciences Engineering Research Council of Canada, NSERC, and also we had a wonderful equipment grant, which we're going to talk about, help us do our research, from Canada Foundation for Innovation. This program is also collaborative work between Natural Resources Canada. We've had assistance from Department of Fisheries and Oceans and Geological Survey of Canada. So it's really been a privilege for us to be involved in this collaborative program. It's often me that has the opportunity to stand up here and talk about it, but definitely many acknowledgements and thanks to the scientists, technicians, officers and crews of Canadian Coast Guard ship Vector, which is our research vessel. And without that whole team, there's no way I'd be standing up here talking about this work. So, who's felt an earthquake recently? Did anybody? Where did you find it, Kathy? Right, exactly, and here we go. What I'm doing is putting up on the board red, yellow, and there we go. That's the one that Kathy's talking about. These are recent earthquakes which has been in the news. Mr. Red Star up there, that's a magnitude 7.7, occurred on October the 27th, which most of us are probably aware of. People living in coastal communities certainly were, because a tsunami warning went out from that earthquake. And there was some tsunami impact on the west coast of Hawaii, but it's a very unpopulated, low infrastructure, no infrastructure area. So that earthquake was the second largest recorded earthquake in what we call our instrument record, which is the length of time that we've had seismographs actually monitoring ground shaking. The first one in Victoria was installed in 1898. So that's the second largest earthquake in over 100 years. The first largest was almost exactly in that place, magnitude 8.1, and that happened back in the 1980s. So this was pretty exciting for those of us who study earthquakes. And then following quickly on the heels of that, we had one offshore Vancouver Island, December the 23rd, and then we had magnitude 3.3 that many of us felt just off of Sydney. So we've had a lot of activity. Our earthquake that we now call the Haida Gwaii earthquake is what we refer to as a designer earthquake. We love these. Very powerful earthquakes. Nobody was killed. No infrastructure was damaged, except many First Nations and local people on Haida Gwaii might argue with me. You may have heard that these very famous hot springs, which have a lot of spiritual meaning to the local people and have for many thousands of years, dried up on the day of that earthquake. So the scientific explanation is that rocks beneath the earth, of course, are moving along fault lines during the earthquake, and groundwater that was being heated up from closer to the Earth's mantle, the plumbing basically was shut off because of the way the cracks in the rock moved. And I have been told that the mythology from First Nations on Haida Gwaii does have some information that the hot springs have sporadically dried up and come back over many millennia. So we shall see. Many of my colleagues, I'm what's called a visiting scientist at Institute of Ocean Sciences, Geological Survey of Canada, and that's just out by the airport. That's where Canada's seismologists, and those are scientists who register and study ground shaking from all over the planet. And if you ever want to do a tour of that equipment, you can ask for a tour at Institute of Ocean Sciences. So that's where our seismologists in Canada are working. So they quickly mobilized to Haida Gwaii, and we have now set up another 15 ground motion sensors, and that's a CBC camera crew. Seismologists, they're kind of the sexy James Bond scientists. They've got the pagers on, the earthquake happens, CBC talks to them. They're pretty cool guys. And what they did is they went out to Haida Gwaii, had a look at geologic evidence. These are landslides right here that have occurred into the water. And just keep that image in mind as we go along. And that's one of the keys that we look for in the geologic record. Can we see at the bottom of nearshore areas sediment disturbance that might be related to earthquakes? And also our major research ship, the Tully, just came back yesterday. They went out right after that earthquake, put in on the bottom of the ocean, right along that fault line, seismometers just after the earthquake, and they just went to pick them up, and they're very, very excited about the data. So that's our designer earthquake. It tells us a lot about how the crust is moving, aftershocks, etc. So that was really exciting. So it seems like we've had a lot of earthquake activity, but guess what? These are the epicenters of earthquakes locally recorded from 1895, and I'm not sure what that means because the first seismograph was 1898. However, long time ago to 2004, we actually get about 300 earthquakes a year in our local area. Many of them we won't feel because they're very low magnitude or they're offshore and they're too far away from us to feel. So geologically speaking, this is a very seismically active area. And of course, we all want to know the answer to that question. When is the next big one coming? And if we know that, how big is it? How often is it going to happen? When is it going to happen? And so throughout this talk, I'm going to give you some little hints about how, as scientists, we're trying very hard on this coast to answer that question, to help the public, policymakers, and planners to actually plan our sustainable communities in a seismically active area. So what's going on? Many of you might be, and there we are in the red star today looking at us from outer space. Many of you probably are aware that tectonically speaking, here in Victoria, we're sitting on the edge of the Pacific plate of the Earth's crust that is subducting down underneath the North American plate. And I want you to think about this melting that occurs right here at about 20 kilometers below the Earth's surface. We're going to talk about that in a moment as well. So that's our tectonic setting. The ocean crust is going down, and we hope it's going down very smoothly, but we actually know by ground motion sensors and strain gauges and seismographs that it gets stuck. okay? And these very large, massive magnitude 8 and 9, what we call subduction zone earthquakes, occur in geologic time when that sticking releases, and that releases huge amounts of energy. And so there's just a very basic diagram of what we mean by plate tectonics. As many of you know, the continents are actually always scooting around the planet. We kind of know that, but guess what? When I did my undergrad geoscience education back in the Cretaceous, we actually were taught plate tectonics as a new evolving theory, and the old theory, which was called Molas and Flisch, which is now discounted. But I just wanted to point out that plate tectonics and our knowledge that we actually have a subduction zone here dates back to really the late 1980s, which is quite incredible. So what was our knowledge? So now we know that, we have an instrument record, we can measure that subducting zone. This is very recent information, scientifically speaking. However, First Nations along this coast who have lived here at least 8,000 years and probably millennia before that have a very rich mythology of ground shaking and huge ocean waves coming ashore. So we know that before historic time, we were getting these massive shaking events and probably tsunami coming from the ocean. How else can we say, yeah, we actually do get these huge magnitude 8 and 9 earthquakes on our coast? This is a very famous example, and it's called the Orphan Tsunami. We know it happened, try again. January 26, 1700 AD, about 300 years ago, 9 p.m. How did we figure that out? There was a massive, probably magnitude 9 earthquake along our coast. We know that because over there in Japan, they had a huge tsunami wave. And when it came ashore, where it came ashore, and how high the wave was very carefully recorded by monks in Japan. So computer modelers, we have now back calculated that to have, and this is a very famous artist rendering of that tsunami wave coming ashore in 1700 AD in Japan, we've been able to back calculate that, and we think the epicenter of that massive earthquake that created that tsunami that went all the way over to Japan was somewhere just off our coast. So these are examples of what we call our historical record of major subduction zone earthquakes on this coast. We know they happen. We haven't had one during our instrument record, but we do know they happen. And this is the sort of work that I'm involved in. The geologic record, what we call the paleo or past seismic record, also records, like a library, these events. This is a tidal marsh out in the Port Alberni area in West Coast Vancouver Island. And a tidal marsh is growing away 300-400 years ago, and you got your roots and your organic soil. Boom, sand layer right across the marsh. And then the marsh reestablishes itself. And we can actually go in and we can date those sand layers. We can find marine foraminifera in those sand layers and prove that that sand layer came from the ocean. So we have areas all along the west coast of Vancouver Island and many more along the west coast of the United States that give us this paleoseismic evidence of that 1700 AD earthquake. So we can come up with diagrams like this. Every single one of these little stars is one of these little sand layers and or archaeological evidence of a native village, for example, being destroyed with that sand layer on top of it. So we can go along and go, you know what, we probably do get tsunamis along this coast. Obviously something that we need to think about and plan for, and that's the work that I'm involved in. How can we more specifically quantify and time these events that can impact our coast? So let's look a little bit more deeply into the tectonics. Here we have a block diagram. We're here in Vancouver Island. There's our subducting zone. And you can read for yourself, there's a number of historical, measured in the instrument record, earthquakes. Some of them are crustal earthquakes, which are just up on the top of the crust, which is kind of moving around. And others, the big ones we worry about, happen on the subducting plate much more deeply, much more energy, and that's where we believe the 1700 AD earthquake happened. So let's have a look at the earthquakes that we've just had in the last number of months. Here's the big one. Let's just think about this. Now we get into the complex part of it. This is the subduction zone. It actually ends, there's the end of the subduction zone, and we call it the Cascadia subduction zone. But the Earth's plates are still trying to move around, and it switches from a subduction zone right here into what we call a transverse fault, and there's the motion arrows. So the fault along which we've just had our recent earthquakes is actually moving this way, laterally, okay, instead of underneath. In a moment, we'll talk about why it's the subduction zone earthquakes that create these huge tsunamis. Plates that are moving back, across in a transverse direction normally do not create tsunamis quite as large, and we'll talk about that in a moment. Also, here we go, the subduction zone, let's extend it. It goes all the way down to California, where again it trends inland here and turns into another transverse fault, and there it is right there, the San Andreas Fault that goes through San Francisco, Los Angeles, California. Anybody seen that when you're flying down to Vegas or whatever? Yeah. Very, very obvious expression of that fault. That fault generated a very famous earthquake in San Francisco in 1907, magnitude 7.9. Not a subducting zone earthquake, transverse earthquake. Epicenter very close to San Francisco. 80% of the city was destroyed, mostly because of the risk of fire. Good news for us, 2 years ago, Vancouver switched their fire pumping system so that they could actually pump from the ocean. So this was a really big problem. It's been a problem in earthquakes in Japan as well. How do you put out the fires? Buildings and people can actually survive. In many places, the shaking, but the fire is level 2 of what we have to think about in sustainable communities. So there's our potential rupture zone. Our questions scientifically are, does the entire zone rupture? Does part of the zone rupture when that energy is released? And if so, how can we tell that? And to do that, we need to look way back in geologic time, thousands of years. And as if we're not worried enough as it is already, there are other geohazards, what we call geohazards, that we have to think about and give information to planners of sustainable communities. See, oops, see these volcanoes? Look at them. They're all in a line, including Mount Baker. See that? Now, do you remember way back that gorgeous picture of the subduction zone and it goes on fire about 25 kilometers? These volcanoes are all located exactly 25 kilometers above the subduction zone. And that's the depth at which the Earth crust melts, and any water in it, water vapor, it finds its way up through cracks in the rocks, and it has created these chains of volcanoes. Geologically speaking, they are very young. They were all created in the last 10,000 years. They're also geologically active volcanoes. Mount Baker had a steaming event back in the 1970s. It had a small eruption around the turn of the century. And those of us old enough to remember Mount St. Helens, yeah, it actually erupted. So communities such as Bellingham, Abbotsford, actually do have plans for if there were to be an eruption of Mount Baker, because we have what are called lahars, which is debris flows and water and ash that can actually result from volcanoes. It's also good news, these volcanoes, for scientists, because there you go, these are very famous volcanic eruptions back through geologic time. The big one was Crater Lake, which actually blew the entire top off that volcano. Some of you may have visited Crater Lake. That happened about 7,700 years ago, and the ash cloud is in pink. So geologists, that's the sort of stuff that we do, walk around looking for evidence of ash cloud. So ash from that eruption has been found in this pink area. And here's one of our marine sediment cores taken from our main study site, right out there, west coast of Vancouver Island, where we call Effingham Inlet, and we found the ash right there about 20 meters down in a core. But this is fantastic because we can very easily date exactly when a volcano erupted. There's a whole explanation of how we look at the glass shards and when and how they were crystallized. So geologists such as myself, we really like to find volcanic ash in our cores because that helps precisely date the age of the sediments and the age of disturbed sediments that we think are associated with earthquakes. We didn't expect, and guess what? You can see that we thought the extent of the ash cloud was pretty much just Victoria, but now we're able to draw the ash cloud much bigger. So that's 20 meters down in the sediment core. Isn't that incredible? So this whole area probably would have been blanketed with a couple of meters of ash after that volcanic eruption down here in Crater Lake. So let's talk a little bit about tsunami and why we don't worry quite as much that that transverse fault where we've had a recent earthquakes is going to create a tsunami. A tsunami happens when we have this downward motion, and here we go, block diagram of Vancouver Island. Pressure is building up. The center of Vancouver Island is just slightly rising. Really good news, because sea level is rising very rapidly because of global climate change. Vancouver Island is moving up more quickly than sea level rise. Very complex piece of information to translate to the public, so the public doesn't go, scientists have no idea what they're talking about with respect to global sea level rise. So the planet has her own ways of doing things. If we have an earthquake, we know that sea level can change by up to 4 meters during that earthquake. So when the earthquake actually happens, the rupture happens, and that pressure subsides, you can see that local sea levels can actually change. And we know that can happen. Out at Island View Beach, there's actually a drowned forest floor at certain times of the year that's uncovered by the sand. We think there was an earthquake about 1,200 years ago, dropped sea level about 1 meter, and the forest that was standing there was instantly killed. And you can actually just walk over the roots of the trees. It's really quite stunning. I call it the baby in the bathtub effect. You need to have this vertical displacement, and the seawater is basically going, what? It's like dropping the baby in the bathtub. Not that I ever did that. And the water, and so this huge energy, and here we go, this is the 2004 Sumatra earthquake, generated that phenomenal tsunami throughout the Indian Ocean. There's that stunning movie out right now about that tsunami. I am not going to see it. Yeah, certainly not something to joke about. An issue of geohazard sustainability. So many people were killed in the Indian Ocean theater because they did not have a distant or early warning system. We have had that in the Pacific and the Atlantic since the Second World War. Why did we not have it in the Indian Ocean? Well, probably first and third world politics. There is now a distant early warning system. There was enough time for many tens of thousands of people who were killed during that tsunami to actually get to higher ground, and they didn't, because this is what is called a far field tsunami. People over here in Africa would not have felt the earthquake, but they are impacted. It's called far field tsunami. This would be a near field tsunami along Indonesia. They felt the earthquake, get to higher ground. You need a distant early warning system, a plan, and communications to get people away from the shore for the far field tsunami case. And here you can, I was doing this last night, oh my gosh, you can Google around the internet now. Isn't YouTube powerful? And watch some of the videos of just these phenomenally huge waves coming in. Something also to know, you can see here how the intertidal zone, and right here as well, very, very wide. What happens? Same thing as a small wave on a beach. First the wave goes out, and then it comes in. So you have a really big wave coming in. The first thing you're going to see is the tide going way, 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 way out. If you ever notice that, do not wander out to the edge of the ocean. Go the other way. Yeah, and so there's the tectonic diagram of what happened. This was not a designer earthquake because of the devastation afterwards. However, it was very powerful scientifically. What we found out was this entire subduction zone ruptured at the same time. Up until then, scientifically, we thought that subduction zones, such as our own Cascadia subduction zone, would only rupture in pieces. We didn't know that the whole darn thing could go. So that was a very interesting piece of information. Little FYI, our own subduction zone from northern Vancouver Island down to San Francisco is exactly the same length as this subduction zone. So we found that piece of information out, that some of our Cascadia subduction zone earthquakes, it can be the entire zone that's rupturing. And this is something that we're really looking into scientifically. Tohoku, Japan, March the 11th, magnitude 9. Those phenomenal pictures. I think for myself, this one had a huge impact around the world because this was the first time a first world country was impacted by this natural disaster. And I think it's just the way our minds work. You can look at Haiti and how they went through their crustal earthquake and the terrible devastation of that society. It's something else. It gets a bit closer to home, unfortunately, but it does when you see a nuclear power plant disabled, where there's first world infrastructure, etc. So we learned a lot as well about the Tohoku, Japan earthquake. We're still learning it on our coast. This is a picture of debris from that debris field from the far field tsunami, which has just begun to come ashore on Haida Gwaii. We have a really major problem. With that, there's a lot of huge debris, for example, metal train containers and ship containers that are out there on the coast. They've been sighted by Coast Guard and fishermen, and they're just underneath the water, so they've created a navigational hazard on our coast as well. Sustainable planning, how do we deal with this? How do small communities on Haida Gwaii deal with this? How do you get there? How do you get a big train container off a beach on the west coast of Haida Gwaii, and should we do that? Really interesting question, and thanks a lot of our undergrad students are here. A lot of these questions will probably fill up the remainder of your career. How are we going to deal with these things? And one of our Coast Guard captains that I've worked with for many years just popped into my office to say hello a while ago at iOS, and he was telling me about seeing the Japanese couches and refrigerators floating out there offshore. And I was saying, wow, you know, it's such a problem. How are we going to deal with this? And he said to me, Audrey, it's a fantastic thing because it reminds us that we are all connected. And I thought, I like that. It's so true. Earthquakes and geohazards come from the planet, and one could argue that they are a planetary responsibility. It's not something that's just happening over there in Japan. It's impacting us as well. And I actually think that that's helping us to progress in areas, all areas of environmental issues, particularly climate change. It's global. It happens on timescales that are so difficult for us to understand. Yet, as an earthquake and tsunami, the chance of it happening in our lifetime might be very small, but if it does happen, the impact is so huge. How do we figure that out? How do we deal with our resources? How do we manage risk assessment? How do we deal with sustainable planning? So you can look at this yourself. This is where we're going scientifically, and this gives you an idea. I can't even really picture it in my mind without experiencing it, how huge these massive, massive earthquakes must be. They make our planet essentially ring like a bell. And that's what seismologists do. They pick up the energy waves on seismographs all the way around the world, and by methods of triangulation, they're able to find where the epicenter of earthquakes are and how powerful they are. And that information comes in now almost instantaneously after these earthquakes. So this graphic up here shows us that the largest earthquake ever recorded on the planet in our instrument record, 1960 in Chile, but magnitude 9.2, enough energy was released there to equal all of the energy use in the United States for 1 year. How can you even think what that is? Just absolutely massive. This is something else we're dealing with on our coast. This is the length of the fault rupture in the Sumatra earthquake, Indian Ocean 2004. This is the length of the Tohoku earthquake fault zone in 2011. And that's something that we're really trying to get a handle on in Cascadia. When it ruptures, how long is the rupture length? Where does it happen? Which parts of that rupture are tsunamigenic? So just in the second half, we're going to talk more specifically about how we're researching this on this coast. Does this give you a little bit of comfort? There's lots of machinery, and you know, we're going all over the place. And really trying to get on top of this information. But before we get into that, this came to me, and it's Great East Japan, which is the Tohoku earthquake, which happened in March 2011, recovery and reconstruction by the OYO Corporation in Japan, and that's a consortium of companies involved in the cleanup, in risk assessment, and prevention for the next earthquake. And this is just an excerpt written by Masaru Narita, who is the president of those companies. And it's a bit shaky in the translation, but he says, while the earthquake of a magnitude of 9, as this time had been reported to have happened in the past, with resultant tsunami in the scholars' circle, such research results and corresponding implications were not sufficiently reflected in the damage remediation measures when it did happen. I believe, therefore, that many of us had to face a situation which had never been anticipated, nor had we been prepared, the fact that features in this tragic disaster. What he's essentially getting at is, there's kind of a joke in my science world, we actually joke as scientists, that for every seismologist in Canada and the United States, there's a seismological research institute in Japan. They are all over it. They even, all of their fire stations are hooked up to seismometers, and if there's any ground shaking, metal bars come and prop open the doors of fire stations in Japan, so that if the building is damaged, they can still get those fire engines and emergency relief out there. They are pretty darn good, and boy, do they know how to move when there's a tsunami warning as well. And many of you may have seen or heard that a lot of people were killed in the Tohoku earthquake because they were actually where they should be in the disaster relief centers, but they were within the tsunami run-up zone. And guess what? Geologists who studied the paleoseismic record, and that means where is the maximum tsunami run-up from the coast in geologic time, knew that the tsunami was going to come higher than the calculations from the instrument record. So that's what this is alluding to. And we do this all the time in science. We're in our little silos, we don't talk to each other, and if we do, it's not at the right time, or we don't give each other the pieces of information that we need. There actually was a lot of published paleoseismic information that that tsunami run-up was much higher than had been calculated from all of the modeling of potential earthquakes from the instrument record. We're doing the same thing here in Canada. We love looking at our computers and all the data that we can measure, but we have to go back in time because our instrument record is such a tiny slice of geologic time. So that's the aim of this research program. It goes back to an ocean drilling program, Leg 169S, which I was not involved in August 1996 in our own Saanich Inlet. We're going to talk a bit about why the sediments in coastal British Columbia are a really great place to look for earthquakes in the past, just in a moment. And the JOIDES resolution, these are international drill ships, and you can see by the height of the drilling rig from the ship, they can take really, really long sediment cores. And Saanich Inlet, they got in there, they had wonderful cores. Some of you who lived here at that time might remember some of the newspaper reports. Very, very interesting scientific expedition. The sediments in Saanich Inlet record both crustal earthquakes and subduction zone earthquakes happening in this area approximately every 500 years. That's what we learned from Saanich Inlet. We wanted to get out here on the outer coast of Vancouver Island. In this area here, there's so much crustal earthquakes happening. You may have recalled that from the polka dot map a while ago. We wanted to try and get a record that didn't have quite so many crustal earthquakes and was starting to record just the major subduction zone earthquakes. So round we went. Marion Dufresne, 2002, another international drill ship, took a core in Effingham Inlet. If you want to know how big Effingham Inlet is, you pretty much have to put soap on the side of that ship and scrape it in there. They had to back the ship in there, and we took this fabulous core, 60-meter core, went right down, smacked on bedrock. So we got all of the sediments, 12,000 years back to the end of the last glaciation. We've been studying that core since 2002. That's our main study site. From there, we've been taking the information that we have learned about how to look for earthquakes in sediments all the way up the coast, west coast of Vancouver Island, and some lovely inlets here on the mainland coast. That work has been done from CCGS Vector. We can't take cores that are 40 or 50 meters long. You can only do that with an international drill ship. But from our little ship, we can take cores 10 meters long. And if we pick our coring location properly, That gets us back 6,000 to 8,000 years in the geologic record. So that's what we've been up to. This is the basic premise. What we're looking at here is the British Columbia coast from space, okay? Orient yourself. We're right down here off the map. There's Haida Gwaii. This is taken from the Thematic Mapper satellite, July 2002, and it's color-coded to chlorophyll. Diatoms are phytoplankton, which bloom in the spring and summer, and they contain chlorophyll because they photosynthesize. So this satellite can read the amount of chlorophyll in surface waters, spring and summer. So red is a lot of diatoms, green not so many, and out here there's these guys having a party out here in the ocean. So you can see that the west coast of Vancouver Island and our inlets, we have fabulous blooms of diatoms in spring and summer. So we go from satellite right back down to backscatter electron microscope. These are single-celled creatures, 4,000 different species. Micropaleontologists can actually identify what the sunlight level was, what the water salinity was. From there, we can back calculate what upwelling and nutrient was on our coast way back in time. It's just phenomenal record. So that's what's being raining down to the bottom of our inlets. We can't see it, but it's happening in the summer. In the winter, our inlets along the west coast of Vancouver Island, it's raining like stink, just the way it is here. Anybody seen Saanich Inlet look like chocolate milk? Driving up in the Malahat? Exactly. So what happens, the sediments at the bottom of our inlets look like this. So this is a 20 centimeter piece of an X-ray of a core. Okay, it represents, and you can count them up, about 120 years of sedimentation about 4,000 years ago in Effingham Inlet, west coast Vancouver Island. So you can actually measure and get in there and identify the white layers are the diatoms and the dark layer is the thickness of rainfall in the winter. So we've been able to develop also a very precise paleoclimate record of this coast, which we use as a backdrop to the current climate change. Fabulous paleo-environmental study site. For example, you don't have to be a geologist to have a look and see right there, which is 4,000 years ago, sedimentation on the coast changed. The diatom blooms, these big white layers, which have been happening happily for 82 years, failed. Lots more rainfall. So it's 82 years of sedimentation here and 130 years of sedimentation there. And this represents an abrupt climate change. So that's a whole nother talk, but this is the sediment column that we're looking for. Guess what? That lovely annual, nice, quiet, minding its own business sedimentation is hugely disrupted when the ground is shaken by earthquakes. So that's kind of an elegant record for our earthquakes, and this is what we're looking at here. We have various areas in our cores. Again, this is an X-ray of a core. Sometimes the sediments are disrupted by incoming bottom currents that just mix up the sediments and redeposit them. That's very important. You can go back and look at extreme storm fields in the past, looking at what we call lithofacies, but we have other units that are deposited, we know, by ground shaking. So that's the basic premise of the work that we do. Sounds easy. Well, here we go. Actually, finding those coring sites has taken us about 10 years, since 2002, when our main study site. We do surveys that give us the sub-bottom profile of what sediments look like below the ocean. Many of our cruises collect only sub-bottom profile, for example, and we spend a year analyzing that. We get the ship again, then we go back out and do our piston coring. We also, and that samples the surface sediments, and remember this here, this is a pipe that goes all the way down the ship, about 10 meters long. It's about a half a ton, we call it a pig on the head of it, and that's slammed into the sediment. So this is big cranes, lots of stuff happening, very heavyweight way of sampling ocean sediments. We also have equipment that measures coastal ocean dynamics that helps us to find water columns where those types of sediments like to be deposited, those nice layered sediments. And we also have, several of our cruises have been dedicated to this sort of imagery. This is multi-beam surveying. We have a bottom sonar. It's got 160 beams. We basically get in there and we mow the lawn. Got 9 computers, collects all this information, and it generates what looks like an aerial photograph of the bottom. Oops. And this is a pretty cool one. This is Alberni Inlet, just out of Port Alberni. And just right here, you can see there's a very faint kind of yellow conical feature there. And over here, we interpret this as a glacial moraine from the last glaciation that has been broken through on the bottom by a tsunami coming up Alberni Inlet. And that broke through the moraine on the bottom and created this sort of wave structure on the bottom. And if anybody knows Alberni Inlet, you ever taken the ferry or a ship or a small boat down Alberni Inlet, it's really hard to get past this spot because all the fishermen are there. And they're there because this feature on the bottom has created this wonderful ecosystem for rockfish and salmon and phytoplankton. Pretty cool. That's just an aside. We also have equipment. This wonderful grant that we got from Canada Foundation from Innovation helped us to create this equipment. It's called a freeze core. Looks like a big popsicle, which is actually what it is, to sample the surface sediments. The piston coring equipment that I showed you, it's so powerful to get that piston core into the sediments, it actually smashes through the top 2 or 3 meters. So we're losing about the top 2,000 years of Earth history. Not good. That's something we really want to be looking at. So we've invented over many different years of trying out this equipment, and it was the CFI that allowed us to have the money to actually create this equipment. It's a core barrel. We fill it up with a slurry of dry ice, and it's white here because it's actually frozen as it's going overboard. We put it in the bottom, we leave it there for half an hour. The sediment, it just goes in very gently. The sediments freeze to the outside, and then you gently pick it up to the surface, and you end up with these wonderful cores, and there you can see these annual laminations. So it's the piston coring operation to sample the deeper sediments, and isn't that gorgeous? Isn't that beautiful? Oh, is it just me, or is that amazing? This is a core from Saanich Inlet. So you can see the summer and spring diatom layers. Some of these cores are so wonderful, you can actually see multiple blooms happening in the spring and summer. You can get in there and identify what those little critters are. Just an incredible record. So we match the freeze core with the piston core, and if we're really lucky, and sometimes it'll take a whole cruise, and Deb knows this one, to fool around with the equipment and the gear and the weather, we can get a core in a certain place that will go from the surface right down to about 8,000 years ago. So here we are. We're tired even talking about this. Back in 2005, we used this technique to try and find what we call modern analogs. Can we go into the sediment record and see what earthquakes that we have actually recorded look like in sediment? If we can figure that out, then we can go down core and go, yeah, that sediment disturbance looks exactly like something we recorded in the instrument record. We're on the right track. We had a very large N7.2 earthquake, central Vancouver Island, 1946. Everywhere we go on the coast, we see this big, what we call massive unit. There's the laminations on top of it, and there's the laminations underneath it. And this unit here was emplaced during that earthquake. We see that in all the inlets where we go. So we go, now we know what that looks like. Guess what else we can see? Let's just back up. That one, every place we see it, is about 50 centimeters long in our freeze cores. And here we have that major 1700 AD earthquake. And the sediment disturbance from that is only 10 centimeters thick. Why? So it's a big question that we have. What inlet is recording what? Is the size of the disturbance associated with the size of the earthquake? You can see all these questions that start coming out. And to answer those questions, what we really need is the regional record. We need many, many, many different cores all the way up the north side of Vancouver Island. That's what we're working on now. Some of the other CFI equipment, which gives us these wonderful, we call them wigglegrams, we acquired in 2009, and here we have it at sea. What it is, it's a track. You can put the core in it, and lots of different sensors measure physical and chemical properties of the sediment. It's a so-called automated way to actually run a lot of cores. So it's taken us up to now, basically, to get our methodology and to acquire this piece of equipment. And I would just like to point out here, this is Malcolm Nicol, who is our BSc graduate in 2010, who was funded on this grant to work with me and my colleagues at Institute of Ocean Sciences for a year and a half. And he helped us to set up this beautiful lab. And there's our piece of equipment that we can take to sea as well. And I think we're really proud of this. It's a collaborative core logging lab. It lives out at the Institute of Ocean Sciences, and we contributed through Royal Roads and CFI the equipment, and Geological Survey of Canada has contributed the room, and it's a lead-lined room because we have radiation sources on this equipment, and they also contributed the computer staff, the admin staff, the security, etc., things that we actually can't support here at Royal Roads University. And why would you? It's a wonderful, wonderful way to have all sorts of scientists on this coast working. Why would the Canadian taxpayer just fund me with a lab here that only I can use? So that lab, with much gratitude to Malcolm Nicol, who worked with us for a year setting up that lab, he just did a yeoman's job helping us with that, opened a year ago. Since then, 13 research groups have used the lab. Over 300 meters of core have been logged, so that's pretty cool. Not just our own group, but many others. Here's, Leslie knows these people. It's a multidisciplinary lab. These are some of our archaeologist collaborators. These are archaeology cores from middens along the west coast of Vancouver Island. And there you go, that's us actually sampling those cores. And you can see that archaeological middens almost look like our laminated cores. They too are recording what the people were eating and the changes in what people were eating over time. So it's been really fun to do this collaborative work. What the heck is this? Never put up a slide that looks like this. So this is where we are now. After 10 years on this research program, our equipment allows us to sample all of these different properties in our cores. We match up these wigglograms, and now we're at an international standard. This is what the big boys do around the world. We're looking at marine sediment cores. We actually have quantitative measures that we can get in there and go, that is actually part of the sediment column. That is what we call a seismite, or it is recording an earthquake. So it's taken us 10 years to prove to ourselves that that's what we do. Another tricky element here is that, of course, we had glaciers on this coast, 2 kilometers of our ice over our head, standing right here 10,000 years ago. And this is Effingham Inlet today, but it looked like this inlet in Alaska about 10,000 years ago. There was so much ice as glaciers were receding that the crust of the earth was actually depressed. It took 25,000 years for that ice to build up. It melted in 300 years. Something else the planet likes to do. It takes a long time to cool down. It likes to heat up really quickly. So suddenly the Earth is actually depressed. Guess what that does to sea levels along this coast? Well, about 6,000 years ago, sea levels were going up and down by several hundred meters. And this is actually recorded in our sediment cores. And we had to get that out of the record, so to speak, so that we know we're looking at normal sedimentation and earthquakes and not some artifact of changing sea levels. So here we go, just orient yourself. There's our study site. Coming down here, Ucluelet, Tofino, Pacific Rim National Park in gorgeous Barkley Sound, Effingham Inlet. That's what it looks like today. This is what it looked like 10,000 years ago, because sea level was much lower. Okay, the crust was depressed. The ice had just started to disappear. There wasn't as much water in seas around the planet at that time because it was still all locked up in the glacial ice caps. So this is really fun to do. Pick a spot that you like to look at. Isn't that interesting? Yeah. So let's have a look here. The archaeological cores that we were just looking at came from Diana Island. People were living on this coast during the time of the sea level change. So Diana Island is now an island, but First Nations living here 10,000 years ago, to them it was a peninsula. Isn't that interesting? So interpreting the geologic record and the human record along our coast means that we actually have to figure out what we call the paleo sea level curve. And if you're not asleep by now, you're going to be asleep when you look at this one. But this is just stepping along in our work. By 2008, we were able to get that information and look at our sea level curve and determine that sea level stabilized on our coast about 6,000 years ago. So we're able to look at sediments from about 6,000 years ago to the present, and we're looking at an environment that essentially looks the same thing as it does now. We really don't know what this glacio-isostatic compression and rebound was, how that was interacting with the subduction zone. Probably was. We don't really know that. So we're really looking about the last 6,000 years, and that's within the coring range of our of the Canadian Coast Guard vector. This is my buddy Dave Spear, Alex Colville moment. What's in the future? Well, obviously we want to know, when is the next big one coming? And like many things, the Americans are way ahead of us on this one. The Americans are really have a good grip on what we call the paleoseismic. Oh, doing a good job here. We're just previewing what we just saw. Try again. Ta-da! There we go. My buddy Chris Goldfinger. He actually looks like James Bond too. Very, very disconcerting. Very famous American geologist. Along the west coast of the United States, we don't know why, but glaciers actually stopped right about the 49th parallel. So the American coastline was never glaciated like our coast. We got no sediments on this coast. They were all scraped out to the ocean. That's why we have a rocky coast. But the American coastline has these major river systems that come down, and they cut these huge channels and these big sedimentary shelves that survived glaciation. And the theory of Goldfinger and his colleagues is that if Cascadia is shaking, then these river channels that go out to the ocean must be depositing what we call turbidites, or big flows of sediment. And if we date those and we can find them all the way along the Cascadia subduction zone, maybe we can tell when we had regional rupture. So this lovely, and Chris always apologizes for this figure, but you know, you could spend the next year looking at this. What this is all about is that they have study sites, and they're all along latitude here, along the American coastline, and they're dating and picking up in these blue and red spots where they actually think we're looking at an earthquake. And then you're doing the Rubik's Cube game, which ones match up. In the last year or so, there we go, that's us in Effingham Inlet. That's the only Canadian study site because we don't have that same sort of depositional environment. So that's why the work that we're doing now is quite important. And if you can squint here as well, there's Vancouver Island, that's the American coastline. This is the modeling that Goldfinger and his group have done. They think the only full Cascadia rupture that they see in the offshore turbidite record was that 1700 AD earthquake. And if you'll notice here as well, you know, you wrote that exam and you just try and avoid the question that you really don't know much about. And that's why our paleoseismic record of Cascadia just kind of ends around Vancouver Island, because we don't know that history, and that's what we're working on right now. So finally, number of ship time grants from NSERC and our CFI equipment and our methodology developed. This past summer, we had a massive cruise all the way up the outside of Vancouver Island. What we've been shooting for about the last 8 or 10 years, we have the methodology and the equipment, and now we have the sediment record for that regional picture of the paleoseismic record. And guess what? Hot off the presses, we're actually, thank goodness, finding them. So this is a seismite or a disturbance that we found in a core from Nootka Sound. Look at the depth, it's about 740 centimeters. And check out this one. Come here, there we go. This, about the same depth in a core, another core, that first core was from Nootka. This is from Herbert Inlet in Clayoquot Sound. We placed the core here because we were looking for a straight shot inlet right in 90 degrees from the subduction zone. We were hoping to capture a tsunami depositing sand at the bottom of the inlet, and there it is. And it's dated at the same time as that seismite we found in Nootka Sound. Very preliminary results. I'll tell you, I had to go home and have a cup of tea. I've never seen anything like that before. Dated 4,200 years ago. What this is showing is a wave coming in from the ocean, bringing sand from the beaches, hitting the end of that inlet, and withdrawing, coming in again, and withdrawing, coming in again, and withdrawing multiple times after one major earthquake. And you can see how the wave is getting farther and farther up into the forest. You've got more soil there. That's the main power of the wave right there. That went way up into the forest, pulled the soil back down again, and then the wave quietly echoed away. So that entire deposit probably represents about 24 hours of Earth history. So we're getting there. So far, we're looking that we had a really big rupture about 4,200 years ago. And here is a simplified version of Chris Goldfinger's record of the paleoseismic history. And there we go. That 4,200 years is also seen all the way down Cascadia. So we're kind of getting there. So I've got a few other slides, but it's about 1 o'clock. So to answer that question, when can we expect the big one? Well, we know now that we're adding some Canadian information from the northern part of the zone, when we get into these graphs all the way down Cascadia, what we know is the longest time between earthquakes, whether they're just partial rupture or full rupture, along Cascadia is 1,000 years. Okay, that's the longest time of quiescence. And the last one we had was 300 years ago. So the answer to that question, as best as we know now, is we could have another subduction zone earthquake tomorrow or 700 years from now. So think about that a little bit in our daily lives. How many resources are we going to put into that? If it happens tomorrow, catastrophic impacts. We are dealing with that with respect to building codes, emergency preparedness, etc. And just remember, you feel powerful ground shaking. Does anybody know what you do? Yeah, that's drop. Get on the ground, get underneath something if you're inside, and hold on, and then get away from the water. We know that we've got about an hour and a half before a tsunami wave generated from our subduction zone will impact Victoria. So you want to get through the shaking, get yourself and your family to higher ground. Just get there. And we will be impacted by the wave hour and a half, 2 hours later, and that will continue to impact the coast for about 24 hours. And I mean, scientifically, I really hope it happens in our lifetime, but yeah. So thanks very much for your attention, and I really hope that no one goes away nervous about these things. I think information really helps us, and believe me, my daughter worries enough for everybody about tsunamis and earthquakes. But it's to know that we shouldn't be building daycare centers below the tsunami run-up zone. Within our families, we should say, if it happens at night, we're going to do this. If it happens during the day, this is something else we're going to do. My dad, at almost 90, lives in a condo with lots of other seniors, and it's his job, if something is to happen, to take the wrench, which is in his apartment, and go downstairs and manually turn off the natural gas. Well, my dad is like the second frailest person on the face of the earth these days, and the wrench is almost as big as he is. And my son said, "Grandpa, just stay put, I'll come do that for you." But those are things that we can do as well. So thanks so much, and if there's any time anyone would like to have a question or email me, I'd be more than happy to answer them. So thanks very much.